Hi everyone. I recently received a comment on one of my videos covering topics with conservation of momentum and conservation of energy that had a really great question that brings up an apparent contradiction with how conservation of energy is applied in different reference frames. I've seen this question and similar ones show up in a lot of different contexts, so I definitely think this is worth going into a bit of detail on. More detail than I would be able to communicate in just a text response. Also, we're going to be going into a little bit more of the math to try to answer this question that's also hard to go into in a text response. So let's look at the comment and the apparent contradiction that it raises. So this was a comment by Technologic. Hey Michael, can I ask you a question? If it takes a liter of fuel for me to reach 100 kilometers an hour, how much fuel would it take for me to reach 200 kilometers an hour? And if I reached 100 kilometers an hour and that brought me to be stationary with respect to someone else, how much fuel would that person say it takes for me to go 100 kilometers an hour relative to them? Assume a perfectly efficient engine, no friction, no air resistance, etc. Okay. So let's start by looking at how we might try to apply kinetic energy to this and the apparent contradiction that we seem to get. So let's say I start just with a object at rest. So my initial velocity, I'm going to say this is state number 1, my velocity is 0. Now, for ease of calculation, instead of going from 100 kilometers an hour to 200 kilometers an hour, I'm just going to change that to 10 meters per second to 20 meters per second. It's the exact same kind of system. It's the same apparent contradiction that comes up. It's just going to make the math a little bit easier to work with. So I'm going to start at 0 meters per second. And let's say this has a mass, let's call this just mass of the car, mc. And the kinetic energy that I start with would just be 1/2 times the mass of the car times the velocity squared, but the velocity is 0, so I start with no kinetic energy. Then later, this car is traveling at 10 meters per second. So we'll call this V2 is 10 meters per second. And if I calculate the kinetic energy, so we'll call this kinetic energy 2, that's going to be 1/2 times the mass of the car times 10 squared. So if I square 10, I get 100, so I'm just going to write this out as 1/2 times the mass of the car times 100. So to go from my rest state to moving at 10 meters per second, I need to add the change in kinetic energy that I need during this segment is going to be 1/2 times the mass of the car times 100. That's how much energy we need. And let's say that 1 liter of fuel gives us that much energy. Okay. Now let's look at the next case. So I then speed up even more. This car speeds up even more and is now going at 20 meters per second. So let's call this V3. And that's going at 20 meters per second. Well, kinetic energy in this state is 1/2 times the mass of the car times 20 squared. And when we plug that in, we're going to get 400 for that 20 squared. And if I look at that section for this second part of the transition, during that change, the amount of energy that I need to add is 1/2 times mc times 300. It's the difference between those. So if I've got 400 that I end up with, but I started with 100 here, that difference is going to be 300. Okay? So in this, it seems that we need 3 times the energy of our original situation. So to go from 0 to 10 meters per second, it takes a certain amount of energy. To go from 10 meters per second to 20 meters per second, I need 3 times more energy than I needed for that first segment. Okay. But here's where the apparent contradiction comes in. So for this part, we're saying, if I reached 100 kilometers an hour and that brought me to be stationary with respect to someone else, how much fuel would that person say it takes me to go 100 kilometers an hour relative to them? So let's say there's a new person here that is already moving at 10 meters per second. Okay. From their perspective, this car is at rest. So from their perspective, the velocity of the car at this point is just 0. Okay. So their kinetic energy in this new person's reference frame would just be 0. Okay. And later on, when we're in this last state, the car, with respect to this person, is going to look like it's moving at 10 meters per second. So that final kinetic energy, from their perspective, is going to be 1/2 times the mass of the car times 10 squared. And when we write that out, we get 1/2 the mass of the car times 100. And for this transition, it looks like our change in energy, how much kinetic energy the car had to gain, is only 1/2 times the mass of the car times 100. So, according to this other person, did I not have to burn as much fuel? You know, the car is burning a certain amount of gasoline, so that should not depend on which frame of reference we're looking at. So we have this apparent contradiction depending on which frame of reference that we're looking at. So how do we resolve this? So first off, it's important to recognize that the kinetic energy of an object does depend on what frame of reference is being used. If I'm standing on the side of a road and see a car drive past, it's moving relative to me, and I would say that it has kinetic energy in my reference frame. If I was inside the car, moving along with the car, then that car, in my moving reference frame, that car wouldn't be moving relative to me. So in that reference frame, I would be able to say the car has no kinetic energy. So yeah, the kinetic energy of an object does depend on the frame of reference. But when we're considering conservation of energy, that needs to be applied to a closed system, which might be more than just the object that we're looking at, than just that car. We need that closed system to make sure that we aren't losing any energy to anything else. No energy is being transferred to some other part of the system that we aren't properly accounting for. And that's going to include any objects that our particular object is interacting with. So in this case of a car driving down the road, what else is going to be included in this closed system? Well, our car operates by converting the chemical energy stored in gasoline to the kinetic energy of the wheels, making them spin. But those wheels are in contact with the road. So as those wheels try to spin, the frictional forces between the wheels and the road, that frictional force as the wheel's trying to spin, that's pushing backwards on the road. And if that wheel is pushing backwards on the road, by Newton's third law, the road is going to push forwards on the car. This is one of Newton's action-reaction pairs. Newton's third law is for every action, for every force, there is an equal and opposite reaction force. So if object A is pushing on object B is pushing back on object A with an exactly opposite force. Equal magnitude, opposite direction. So when the car's wheels try to spin, friction is causing the wheel to push backwards on the road, and the road pushes forwards on the car. It's the same way that you run. If you're trying to run and you push backwards with your legs, the frictional force between your foot and the road surface, that is pushing backwards on the ground, and that means the ground will propel you forwards. So there's an interaction between the wheels and the ground, and that means we need to, in order to use this equation properly, we need to include the effect of the motion of the Earth. Now, you might be quick to say that the motion of the Earth is not going to be affected significantly enough to cause any change in our energy calculations, is it? Well, that's what we're going to look at. we're going to need a couple other tools to help us, including conservation of momentum, momentum being mass times velocity, and saying that in any interaction where there are only internal forces acting between the objects, the total momentum of the system is going to be conserved. And we're also going to be using this squaring A plus B term a lot. This is going to come up in a couple of different sections, so having this binomial formula is going to be really helpful as well. So let's have a look at this system, and let's look from the perspectives of two different observers. Our first observer is going to be at rest with respect to the Earth. So we're going to start out with, let's say, here's the Earth, and here's the car, and nothing is moving to begin with. And then later on, we're going to talk about an observer that's already moving at 10 meters per second to the right. So, observer moving to the right at 10 meters per second. But let's start with the observer that's at rest with respect to the Earth. So initially, nothing is moving. Everything's at rest, so there is no kinetic energy at this part of the motion. The kinetic energy is just equal to zero. Okay. Well, afterwards, again, the car is going to be driving along the road, the car is being propelled forward, but by conservation of momentum, and since there are only internal forces, the force of the car pushing on the Earth and the Earth pushing back on the car, if the car ends up going forwards at 10 meters per second, that means the Earth is going to have to recoil backwards at a velocity equal to 10 meters per second times the mass of the car divided by the mass of the Earth. Now, the mass of the car divided by the mass of the Earth, that is going to be a tiny, tiny value. But let's first check this with conservation of momentum. So initially everything was at rest, so for momentum, we start with 0, and after we've got the mass of the car moving at 10 meters per second to the right, and since this is moving backwards, we have to subtract the momentum of the Earth. The mass of the Earth times the velocity of the Earth, 10 times the mass of the car over the mass of the Earth, and you'll notice that these do in fact cancel out to 0. So the mass of the Earth cancels out. MC times 10 minus MC times 10 gives us 0 back. So we do conserve momentum here. Let me clear that part up just so we are mainly focused on the kinetic energy. So what is the kinetic energy at this point? Well, the kinetic energy is the kinetic energy of the car, 1/2 times the mass of the car times 10 squared, plus the kinetic energy of the Earth, 1/2 times the mass of the Earth times that velocity, 10 times the mass of the car over the mass of the Earth squared. And if we run through these calculations, this is going to be 1/2 times the mass of the car times times 100. And this, if we square this term, one of those masses of the Earth are going to cancel out. And I'm going to write it like this: 1/2 times the mass of the car times 100 times the mass of the car over the mass of the Earth. Okay. Basically, when I square this term, 10 squared gives me 100. When I square the mass of the car, I should have 2 mass of the car terms. In the denominator here, I square the mass of the Earth, and that's going to cancel out with one of these. So we're left with this equation. And going between those 2 points, my change in kinetic energy, how much kinetic energy I've gained going through this motion, is just this expression that we have here. So 1/2 mass of the car times 100 plus 1/2 mass of the car times 100 mass of the car over the mass of the Earth. Again, this mass of the car over the mass of the Earth, this is a tiny, tiny value. So in general, when we're looking in the rest frame of the Earth, just saying that this is my kinetic energy, that's usually going to be just fine. Okay. Let's see what happens in our moving reference frame. Okay. So in this moving reference frame, let's have a look. In my moving reference frame, I'm going to have the Earth and the car. And in this reference frame, the observer that's watching this is already moving to the right at 10 meters per second. So from their perspective, both the Earth and the car are moving backwards at 10 meters per second. Again, from their perspective, if they're moving at 10 meters per second to the right relative to the Earth, then from their perspective, the car and the Earth are both moving backwards at 10 meters per second. So how much kinetic energy do they start with? Well, we've got the kinetic energy of the car, so mass of the car times 10 squared, plus we've got the kinetic energy of the Earth, so 1/2 mass of the Earth times 10 squared. So our total kinetic energy, if we add that up, is going to be 1/2 mass of the car times 10 squared is 100, plus 1/2 mass of the Earth, again, times 100, since 10 squared is still going to be 100. But what do we get in the case where now things are going to be moving? Well, once the car is moving at 10 meters per second to the right, what's going to happen to the car is going to appear to be at rest. So the car's velocity is 0. The Earth's velocity, it still has a bit of recoil, so its velocity is actually going to be 10 plus 10 times the mass of the car over the mass of the Earth. Again, this mass of the car over the mass of the Earth term, that's a really, really, really small value. But let's see how it affects the calculation of our kinetic energy. So in this state, our kinetic energy is just the kinetic energy of the Earth. In this reference frame, the car has no kinetic energy. So, well, our kinetic energy is 1/2 times the mass of the Earth times this velocity squared. So 10 plus 10 mass of the car over the mass of the Earth, all that squared. Here's the first point where we have to use that helpful binomial theorem. Because I can expand this out to say 1/2 times the mass of the Earth times, well, we square the first term, so we get 100. We get 2 times this term times this term. So that's going to be 2 times 10 mass of car over mass of Earth. So this is going to be 200 times the mass of the car over the mass of the Earth. And then this last term squared. So plus 100 mass of the car squared over the mass of the Earth squared. If I expand this out, this is going to be 1/2 mass of the Earth times 100, plus, notice in this second term, the mass of the Earth is going to cancel out, and I'm going to get 1/2 the mass of the car times 200. And in this last term, one of the masses of the Earth is going to cancel, so I can write this as 1/2 the mass of the car times 100, I'm running just a little bit out of space here, times 100 mass of the car over the mass of the Earth. So if I take the difference between these two, because again, I want to figure out what is the change in kinetic energy that we had. Well, in that case, we can say, well, if I'm subtracting those, if I'm doing this final kinetic energy minus the initial kinetic energy, notice both have this 1/2 mass of the Earth times 100. So those terms cancel out. I've got a 1/2 mass of the car times 100. Here I have 1/2 mass of the car times 200. So if I subtract those, the first term I'm going to get is 1/2 the mass of the car times 100. Because again, we had 1/2 mass of the car times 200 minus 1/2 mass of the car times 100. And then I also get this last term, the 1/2 mass of the car times 100 mass of the car over the mass of the Earth. And notice what we get. In this new reference frame, our change in kinetic energy was exactly the same as how much kinetic energy was changed in the original case, when we were looking at this from the frame of reference that was at rest with respect to the Earth. In both cases, doesn't matter which of those reference frames I used, they both agree on how much kinetic energy had to be added to the system. And that kinetic energy is coming from the burning of the gasoline. Okay. So at least in this first part, we do get consistent results between these two different observers. But what about when the car goes to 20 meters per second with respect to the Earth? Well, let's have a look at that one. So I'm going to move this over a little bit more, and let's see what happens when this car is moving now, gains another 10 meters per second, so it's now going 20 meters per second. Let's start with the frame of reference of the person that is at rest with respect to the Earth. So by this point, the car is going to be traveling to the right at 20 meters per second from their perspective. The Earth, again, has to go through a little bit of recoil. So the Earth's motion is going to be, add on another 10 mass of the car over mass of the Earth. So that's going to be 20 mass of the car over the mass of the Earth. And again, let's look at the kinetic energy. So the kinetic energy in this case is 1/2 the mass of the car times 20 squared, plus 1/2 the mass of the Earth. Wish I had a little bit more space on here. My apologies if this is getting a little bit small on here. 20 mass of the car over the mass of the Earth. And we have to square that. Well, I can write this out as 1/2 the mass of the car times 400 plus 1/2 the mass of the car times 400. Let me space this out a little bit more. Times 400 mass of the car over the mass of the Earth. Again, one of those masses of the Earth cancels out, and we're just left with this 1/2 mass of the car times 400 mass of the car over mass of the Earth. Again, this is going to be a tiny, tiny term, but let's include it for now. So in this case, let's compare the change in kinetic energy from this situation over here to this new situation. How much did our kinetic energy change by in this part? So my change in kinetic energy, notice I've got 1/2 mass of the car times 400 minus 1/2 mass of the car times 100. That's going to be 1/2 mass of the car times 300. Plus, well, we have got something similar for here. 1/2 mass of the car times 400 mc over me minus 1/2 mass of the car 100 times mc over me gives us 1/2 mass of the car times 300 mc over me. Again, I know we're getting a little bit into the details. Thank you in advance if you're still bearing with me on this through some of these technical details, but we're going to see something cool happen in just a second. So we have this measurement on how much kinetic energy needs to be added to the system, and again, added by the gasoline that's being used as fuel. The chemical energy is providing this kinetic energy. And again, this last term, because of that mass of the car over the mass of the Earth term, it's so small that we usually just discard that in most of these calculations. But now let's see what's happening in this case where the Earth is, we're now watching this thing from our moving reference frame. Okay. So let's look at what happens. And I'm going to try to fit this nicely on here, but let's see what we can do. So the car has gained another 10 meters per second in this moving reference frame. So now the car's velocity is 10 meters per second. The Earth is still going to go through a little bit of recoil. So in the previous part we had, it's moving at 10 meters per second in this moving reference frame, plus 10 mc over me. Basically, we get another 10 mc over me in order to satisfy conservation of momentum. So we have 10 plus 20 mc over me. Again, that's just required for conservation of momentum. Well, let's go through and calculate what is the total kinetic energy in this system. So this one's going to be a little bit long. I'm going to need a little bit more room, probably over here. So we've got the car. 1/2 times the mass of the car times 10 squared. We've accounted for the car's kinetic energy. For the Earth, we need 1/2 times the mass of the Earth times 10 plus 20 mc over me, all of that squared. Once again, we're going to have to use this binomial theorem. So let's see what we can put together. So for the car, we've just got 1/2 the mass of the car times 100. And I'm going to write this one underneath. So we have plus 1/2 the mass of the Earth. So, sorry, let me make sure that these are clear that this is the mass of the Earth. This binomial theorem, we square the first one. We do 2 times the first term times the second term. So 2 times 10 times 20 is going to give us 400. And that's going to be mc over me. And then we're going to have this last term squared. So 20 squared is 400 times mc squared over the mass of the Earth squared. Again, let me make sure that's clear that that is the mass of the Earth in here. Well, let's see if we can combine some terms. I've got 1/2 times the mass of the Earth times 100. So I've got this term taken care of here. 1/2 times the mass of the Earth times 100. Okay. When I do this term here, so let me highlight which term I'm looking at. I'm going to get 1/2 times the mass of the Earth times 400 mass of the car over mass of the Earth. The mass of the Earth is going to cancel out in that term. So that's going to give me 1/2 times the mass of the car times 400. But I've already got a 1/2 mass of the car times 100. So if I combine these two terms together, that's going to give me 1/2 the mass of the car times 500. 400 from this one, plus 100 from this one. Okay, so we're combining some of those terms. And then over here, we still have 1/2 mass of the Earth times 400, mass of the car squared over mass of the Earth squared. One of those masses of the Earth squared cancel, and I can write this as 1/2 mass of the car times 400 mass of the car over mass of the Earth. Okay, again, I know that was a lot, but again, thank you in advance for bearing with me on that. So now we have to evaluate how did our kinetic energy change from this state over here, where the car was at rest in this moving reference frame and the Earth is moving backwards a little bit, to now the car is moving forwards, the Earth has still recoiled a little bit more, again a tiny, tiny amount, but let's see how the math works out. We want to take the difference in, again, notice that this term, actually we do need that term, so let me, give me 1 second, I'm going to correct this part a bit, just get rid of that line that's kind of crossed out. Okay, because we need that 1/2 mass of the Earth times 100. So we are taking the difference between this whole term and this whole term. And I do apologize that I can't fit them both onto the same screen at once, but notice some of this is going to cancel out right away. So if we put those together, our change in kinetic energy, both of these have a 1/2 mass of the Earth times 100. 1/2 mass of the Earth times 100, 1/2 mass of the Earth times 100. So when I take the difference, those are going to cancel out. So we can get rid of those ones. I've got 1/2 mass of the car times 500 minus 1/2 mass of the car times 200. Well, 500 minus 200 is going to be 1/2 mass of the car times 300. This last term, we've got 1/2 mass of the car times 400 mc over me minus 1/2 mass of the car 100 times mc over me. Well, if I do the 400 minus the 100 and we combine those terms, that's going to give me 1/2 mc times 300 mc over me. So this is the measure in this new reference frame of the total kinetic energy that was coming from the system. And again, that kinetic energy is provided by the burning gasoline, converting that chemical potential energy into the energy of motion, into kinetic energy. And we've looked at it in these two reference frames. So when we consider the entire system, the whole thing that's moving, this includes the Earth, if we're using one of these moving reference frames. Notice, this was the kinetic energy that we had in our reference frame where the Earth, we were at rest with respect to the Earth. This was the kinetic energy that we had to add if I'm in that moving reference frame, the one where I was already moving at 10 meters per second. They are identical. Kinetic energy is conserved if we consider the kinetic energy of the entire system. As long as we have momentum conservation, so we can see how in this case, the Earth is affected by this motion, when we have that conservation of momentum and apply both conservation of momentum to the entire system and conservation of energy to the entire system, all of the objects that are interacting with each other, then it actually doesn't matter which frame of reference we're using. Any of these total changes in kinetic energy are going to be the same. It still takes the same amount of fuel to go from 10 meters per second to 20 meters per second, even if I'm in that moving frame, but we have to consider the entire system. And for this case, that system includes the Earth. So again, we had this apparent contradiction where if I'm just looking at the motion of the car and I'm in this moving reference frame, it seems like I have to add a different amount of energy. But that's because we're not properly considering the entire system that is in motion. If we are moving with respect to the Earth, then in that reference frame, the Earth is gaining a non-negligible amount of that kinetic energy. And we have to take that into account in order to properly keep track of and keep tabs of where all of this energy from the gasoline is going. In both of those cases, the total change in kinetic energy of the system is the same. And again, these last terms on both of these, this one that has the mass of the car over the mass of the Earth, this is tiny. We can safely ignore that term in both of these equations. But we can't ignore some of these intermediate terms when we're considering the mass of the Earth, because the mass of the Earth is super, super large. So when we multiply it by this thing that we were calling tiny, that can again become significant. So again, conservation of energy is accurately applied to any system when in any frame of reference. So we usually are just going to pick the easiest frame of reference. And for this car driving down the road, I would kind of argue that saying the Earth is starting at rest, especially since we can neglect some of these tiny, tiny motions, that's going to be the easier reference frame to work in. But again, if we consider the entire system, it does work in both reference frames. So for your question of, if it takes a liter of fuel for me to reach 100 kilometers an hour, how much would it take me to reach 200 kilometers an hour? Well, the math works out the same way. Going from this one, how much energy was required for the first case, to how much energy was required in the second case, it was triple the fuel. That works for both the frame of reference where the Earth is at rest, and that same thing works for the frame of reference where the observer is already moving to the right. It took, if this is equivalent to 1 liter of fuel, this whole thing would be equivalent to 3 liters of fuel. In both of those cases, we can use conservation of energy and identify the entire system and see that this apparent contradiction doesn't end up being a true contradiction as long as we are including that entire system. Again, this was a really, really good question. And again, I've seen a lot of cases like this or similar to this where that cause a lot of confusion. And again, thank you for bearing with me because there was quite a bit of math in this one. But it is important to kind of go through all of these steps and see exactly how conservation of energy is applied in this kind of relative motion system. So, Technologic, thank you for that question. I hope that this is an interesting response, that you can kind of see how we can actually get conservation of energy in both of those cases. I encourage other people to ask questions in the comments, and we'll call that one good for today. And yeah, thank you for your attention.